In the production environment of a global e-commerce giant, a highly anticipated AI customer service agent began hallucinating wildly just hours after launch. Despite having a state-of-the-art vector database and high-dimensional embeddings, the bot failed to recognize that a major promotional event had ended, leading to thousands of incorrect pricing quotes and a massive data leak of internal logistics notes. This is the invisible wall, the point where traditional retrieval augmented generation, or AGI, fails because the vector data is stale and disconnected from the real-time operational state of the business. Engineers often find that while RAG works perfectly in a notebook or a small-scale POC, it disintegrates when faced with the volatile, high-velocity data environments of an enterprise. We are seeing a critical mismatch between static semantic search and dynamic business logic. By the end of this lecture, you will master the architectural shift required to transform these fragile pipelines into resilient, real-time AI systems that govern data as strictly as a financial ledger. But first, we must examine exactly where the plumbing starts to leak under pressure. When we visualize the traditional RAG pipeline under high-concurrency enterprise loads, we see a sequential breakdown. It starts with the user query being converted into an embedding, but at scale, the latency of the embedding model itself becomes a bottleneck. Then comes the similarity search in the vector DB. If the index isn't optimized for 2026 scale datasets, retrieval speed plummets, but the most significant failure occurs during the augmentation phase. We cram the retrieved documents into a limited context window, which creates retrieval noise where the LLM loses the needle in the haystack. As more users hit the system, the orchestration layer struggles to manage session state and token costs explode while accuracy drops. This linear process retrieve, augment, generate is inherently limited because it lacks a feedback loop and real-time tool access. In professional system design, we call this a tightly coupled failure point where one lag in the vector store cascades into a complete system timeout. This raises a fundamental question. Is the vector-only approach fundamentally flawed for complex reasoning? We are about to look at the architectural counter-evidence that will change how you build. To overcome these challenges, we must evolve toward the 2026 unified AI stack. This isn't just about adding more memory. It's about integrating the Model Context Protocol, MCP, as the standardized bridge between the reasoning engine and the data world. In this new architecture, the vector DB is no longer a static silo. It is part of a dynamic knowledge surface that the LLM can navigate using standardized tool calling. We are moving from a push model, where we force-feed the LLM data, to a pull model, where the LLM intelligently queries the right source at the right time. As an information management professional engineer would emphasize, this requires a shift from simple search to comprehensive data governance and lineage. In this lecture, we will map out every layer, from the optimized embedding strategies to the vector indexing algorithms, and finally, the MCP-based orchestration that prevents the system from breaking. This blueprint is your roadmap to building AI that doesn't just chat but operates with the precision of an enterprise ERP. In the next chapter, we will begin deciphering the 2026 AI stack by looking at the core components of this new world order. In the early stages of the generative AI boom, the industry relied heavily on fine-tuning. We believed that feeding specialized data directly into the model's weights was the ultimate solution. However, we quickly realized that fine-tuning is static, expensive, and prone to catastrophic forgetting. This led to the rise of RAG retrieval augmented generation, which separated the knowledge from the reasoning. By 2025, we saw the emergence of long-context LLMs capable of processing millions of tokens, but even they hit a wall regarding real-time accuracy and cost efficiency. As we move into 2026, the architecture has evolved into hybrid context-aware systems. These systems don't just retrieve, they dynamically synthesize data from vector stores, knowledge graphs, and real-time streams to provide the LLM with a highly curated situational awareness. This shift represents a move from model-centric to data-centric architecture. But wait, having a massive context window or a large vector store doesn't mean the LLM actually understands the data structure. Let's look at the components that bridge this gap in the next scene. The modern AI stack is no longer a monolithic entity. It is a complex layered system architecture. At the base, we have the unstructured data layer, which encompasses everything from PDFs to enterprise Slack logs. This data must undergo tokenization and chunking, a process often underestimated in its complexity. Once processed, it moves to the knowledge base layer, where embeddings turn text into mathematical vectors. This layer acts as the long-term memory of your AI. Above this sits the reasoning engine, usually a large language model like GPT-5 or Claude 4, which interprets the retrieved data. The critical innovation of 2026 is the interface layer, where standardized protocols like MCP ensure that these layers communicate without losing context. Without this structured approach, your AI is just a fancy search engine with a high hallucination rate. If these are the ingredients of a modern stack, how do they actually talk to each other in a production environment without creating a mess of spaghetti code? In a real-world enterprise environment, an LLM doesn't sit in a vacuum. It acts as an orchestrator. Think of the LLM logic as the brain, but for that brain to be useful, it needs hands and eyes. The hands are external tools, APIs, database connectors, and web browsers. The eyes are the data streams coming from your RAG pipeline. This interaction is handled by orchestration frameworks that manage the state, memory, and tool calls. In 2026, we see a heavy shift toward agentic RAG, where the system doesn't just fetch data once. It reasons about what it found, identifies gaps, and fetches more data if needed. This multi-turn interaction requires a robust, high-level system design where every component is modular and replaceable. This looks beautiful on paper, but in production, we often face the silo problem where data cannot flow freely between tools and the model, leading to fragmented context and system failure. Why do 80% of RAG prototypes fail when they hit production? The answer is context fragmentation. In a siloed approach, your vector DB, your SQL database, and your external APIs all have different authentication methods, data schemas, and latency profiles. This creates API chaos, where the developer spends more time writing glue code than improving the AI logic. When an LM tries to access these silos, it receives fragmented snippets of information, leading to what we call contextual drift. In contrast, an integrated architectural approach uses a standardized the model context protocol, MCP, to unify these sources into a single, navigable context for the LLM. By moving from ad hoc connectors to a unified integration layer, we reduce architectural debt and improve the reliability of the system significantly. Is this just a coding problem, or is there a deeper architectural reason why simple prototypes fail at scale? Let's explore the system architect's perspective. From the perspective of a system architect, building an AI application is no different from building any other enterprise system. It must be scalable, reliable, and secure. Moving beyond a simple prototype requires us to think about data gravity, where your data lives affects your latency and cost. We must design for graceful degradation, ensuring that if a vector DB goes down, the system still provides a fallback response. Reliability in 2026 means implementing observability at every step, tracking how embeddings are generated, how search results are ranked, and how the LM utilizes that context. We are shifting from writing scripts to designing systems. This means focusing on the lifecycle of the data and the robustness of the integration protocol. Now that we understand the skeleton of the 2026 AI stack, it's time to zoom into the most critical organ, the heart where embedding and vector DBs live, which we will cover in the next chapter. In the world of 2026 AI architecture, text is no longer just strings, it is geometry. To build a robust RAG pipeline, we must first understand the transformation of unstructured data into high-dimensional vectors. When we embed a piece of text, we are mapping it into a coordinate system where semantic meaning determines its location. Concepts that are similar in meaning are placed closer together. This distance is typically measured using cosine similarity, which calculates the angle between two vectors rather than their magnitude. In high-dimensional spaces often exceeding 1/500 dimensions, this allows the system to understand that king and queen are related in a way that king and apple are not. However, the sheer dimensionality of these vectors creates a curse of dimensionality where traditional search methods fail. This is why specialized mathematical structures are required to keep our retrieval systems both fast and accurate. But how do we decide which mathematical model to trust with our data? The choice of embedding model can make or break your retrieval accuracy before the first query is even run. But wait, is a bigger dimension always better? Let's compare the industry leaders to find out. Choosing the right embedding model is a critical architectural decision that balances performance, cost, and latency. In modern enterprise environments, we often compare giants like OpenAI's Text Embedding 3 series against specialized models like Voyage AI or open-source leaders like BGE. OpenAI's models offer high dimensions and extreme ease of use, but they can be overkill for specific domains like legal or medical data. On the other hand, Voyage AI provides specialized models that often outperform general-purpose ones in niche industry contexts. When evaluating these, experienced architects look beyond just the dimension count. We look at context window size, how much text can be embedded at once, in the model's ability to maintain semantic integrity over long documents. Using a model with too many dimensions can lead to increased storage costs and slower search speeds in your vector DB without a proportional gain in accuracy. It is about finding the Goldilocks zone of dimensionality. This brings us to a critical realization. Even the best model in the world will fail if your data is poorly prepared. Choosing the model is just half the battle. How you slice your data into chunks determines if the LLM actually receives the right context. In the field, I often see RAG systems fail because they use a naive fixed-size chunking strategy. If you cut a sentence in half, you lose its semantic meaning, rendering the embedding useless. As system architects, we must move toward semantic chunking or recursive character splitting. Recursive splitting attempts to keep paragraphs and sentences together by respecting natural delimiters like double newlines or periods. Semantic chunking takes it a step further by using the embedding model itself to detect when the topic of a document changes and splitting at those boundaries. This ensures that every vector in your database represents a complete, coherent thought. Let the code here. Notice how we define overlaps. Overlapping chunks are the safety net of RAG. They ensure that context near a cut point isn't lost. Without proper chunking, your vector search might return the right document but the wrong answer. This technical nuance is what separates a prototype from a production-ready engine. But once you have these perfect chunks and embeddings, where do you put them? The choice of storage is where the true scalability challenge begins. As your AI system scales, the where and how of vector storage becomes a multi-million-dollar question. We classify the current vector DB landscape into three main categories: First, we have managed SaaS solutions like Pinecone. These are built for rapid deployment and massive scale, handling the infrastructure so you can focus on the application. Second, there are open-source native vector DBs like Qdrant and Milvus. These provide immense flexibility and are the preferred choice for architects concerned with data sovereignty or cloud-agnostic deployments. Finally, we have the vector extensions to traditional databases, most notably pvector for PostgreSQL. This is a game changer for many enterprises because it allows you to store your relational metadata and your semantic vectors in the same ACI-compliant database. Choosing between them isn't just about speed, it's about your team's operational maturity and your data's security requirements. For instance, if you're already on AWS RDS, pvector might be your fastest path to production. But beyond the brand name, the real performance of these databases is hidden deep in their indexing algorithms. Let's look under the hood at how they actually find those vectors so quickly. In a database containing millions of vectors, a linear search is impossible. It would take seconds for a single query. This is where approximate nearest neighbor or ANN algorithms come in. The current industry standard is ANSW, or hierarchical navigable small worlds. Imagine a multi-layered graph where the top layers have fewer points for broad navigation, and the bottom layers have all points for precise local search. It's incredibly fast, but consumes significant RAM. Alternatively, IV, or inverted file indexing, clusters the vector space and only searches the most relevant clusters. It's more memory efficient than HSW, but typically slower and slightly less accurate. As an architect, you must weigh precision against latency. If you're building a real-time chat agent, HSW is usually the answer. If you're doing batch processing on billions of records, IVF or even flat indexing might be better. But performance isn't just about the algorithm. It's about finding the pure right answer among millions. This leads to a critical question. How do you choose the right database for your specific enterprise needs? Let's go through the definitive checklist. Selecting a vector DB isn't just a technical choice. It's a strategic one. For enterprise-grade RAG, we look for 4 major pillars. First, hybrid search capability. You need to combine semantic vector search with traditional keyword search, BM25, because sometimes users look for specific product codes or names that embeddings might blur. Second, metadata filtering. Can the database filter by region or security level before it does the vector search? This is vital for multi-tenant applications. Third, scalability. Does it support horizontal sharding when your data grows from 1 million to 1 billion vectors? And finally, security. In 2026, features like role-based access control, RBACs, at the vector level are no longer optional. If your database doesn't support these, you'll end up building complex, buggy middleware to handle authorization. Many teams ignore these boring requirements early on, only to face a total rewrite 6 months later. But even if you have the perfect DB and the perfect index, users might still get irrelevant results. Why? Because vector search has a hidden flaw called the lost in the middle problem. Let's see how the experts solve this with re-ranking. The biggest mistake I see in RAG architecture is assuming that the top 10 results from a vector search are the absolute best. Vector search is great at broad retrieval, but it lacks the fine-grained judgment needed for perfect answers. This is why we use a 2-stage retrieval pattern. Stage 1 uses a fast vector search to get 50 candidates. Stage 2 uses a ranker across encoder model to look at the query and each candidate together and give a precise score. This solves the lost in the middle phenomenon where LLMs struggle with too much context. And another pitfall is ignoring metadata. Your vector DB should know that a document from 2024 is likely more relevant than one from 2019. By implementing re-ranking and smart metadata filtering, you turn a decent RAG into an elite one. We have now covered the engine, the embeddings, and the storage. But here is the problem. This engine is still static. It only knows what you've indexed. What if the answer requires real-time data or an external tool? This is the massive gap that our next chapter's hero, MCP, was born to bridge. Next, we look at how the model context protocol changes the RAG game forever. In the rapidly evolving AI landscape of 2026, we have moved past the era of custom-coded integrations for every single tool. Previously, if you wanted your LLM to interact with a specific SQL database or a private GitHub repository, you had to write bespoke glue code that was often brittle and model-specific. This is where the Model Context Protocol, or MCP, enters the scene as a game changer. MCP is an open standard that enables developers to build secure, two-way connections between their data sources and AI models. Think of it as the USB port for the AI era. It allows a model to understand the schema and capabilities of a remote or local data source without manual prompt engineering for every interaction. By standardizing how context is shared, we ensure that an agentic system can switch between different LLMs, be it Claude, GPT, or an open-source Llama without rewriting the underlying data fetching logic. This architectural abstraction is critical for enterprise-grade systems where data security and interoperability are non-negotiable. But how does this protocol actually move bits and bytes across the wire? Let's look under the technical hood in the next scene. To understand the technical workflow of MCP, we must look at its client-server architecture. In this ecosystem, MCP client is typically the AI application or the LM environment itself, while the MCP server is a lightweight process that sits directly on top of your data source. These two communicate using a structured JSON RPC 2.0 protocol. ensuring that every request and response is strictly typed and predictable. The transport layer is flexible. It can operate over standard input-output for local processes or via server-sent events, SSE, for remote web-based connections. When a model needs to perform a task, it doesn't just guess what to do. It queries the MCP server for its list of tools and resources. The server responds with a clear schema, telling the model exactly what functions are available, such as read file or query database, and what parameters they require. This handshake ensures that the AI's function calling is accurate and stays within the bounds of the system's capabilities. However, knowing the protocol is one thing. Understanding where it actually sits in your production environment is another. Let's examine the stack placement. In a modern AI stack, MCP occupies the critical middleware layer between the intelligence of the LLM and the raw data of your organization. From a system architect's perspective, we no longer want our models to have direct, unmediated access to databases. Instead, we insert MCP as a mediation layer. On the top, we have the intelligence layer consisting of models like Claude 3.5 or GPT-4o. Below that sits the context orchestration layer where MCP lives, managing the flow of information. Below MCP, we find the persistence and action layer, which includes your vector DBs, traditional SQL databases, and even API-based services like Jira or Slack. By placing MCP here, we gain the ability to audit every interaction, enforce security policies, and most importantly, allow the LLM to use tools dynamically based on the user's intent. This setup transforms a passive RAG system into an active agentic system capable of both retrieval and execution. This architectural shift solves the integration headache, but it also forces us to rethink our classic RAG strategies. How do RAG and MCP actually coexist? This is the central question we will answer next. A common point of confusion for architects is whether MCP replaces RAG. The answer is a definitive no. They are complementary technologies that solve different problems. RAG is primarily about finding a needle in a haystack across massive amounts of static, unstructured data. It relies on vector embeddings and similarity searches to find historical context. On the other hand, MCP is designed for dynamic interaction and real-time state. While RAG provides the memory of what happened in the past based on document chunks, MCP provides the eyes and hands to see what is happening right now in a live system and to take action. For example, RAG can find a policy document about how to handle a customer return, while an MCP-connected tool can check the current status of that specific customer's order in a real-time ERP system. Choosing between them is not either-or decision. It is about understanding that RAG is optimized for retrieval scale, whereas MCP is optimized for integration depth and precision. If they serve different purposes, the real magic happens when we make them work together in a single, unified pipeline. In a sophisticated 2026 pipeline, we design systems where RAG and MCP work in tandem to provide a unified context. Imagine a user asking, based on our last project report, what is the current status of the server migration? The system first uses RAG to retrieve the project report from a vector database to understand the background and historical goals. Simultaneously, the LLM uses an MCP server to query the live Jira API or a local Git repository to get the current status of the migration tasks. By merging the historical context from RAG with the live state from MCP, the model can provide an answer that is both deeply informed and perfectly up-to-date. This architectural pattern prevents the hallucination of staleness that often plagues pure RAG systems. We call this hybrid textualization. It ensures that the model isn't just reciting a document, but actually aware of its environment. Theory is fine, but how difficult is it to actually build one of these MCP servers? Let's look at the high-level code structure next. Building an MCP server is surprisingly straightforward thanks to the standardized SDKs provided for Python and TypeScript. In this code example, you can see the fundamental structure. We initialize and make server instance and define a tool. Each tool is defined with a name, a description, and an input schema using JSON schema. This description is vital. It's what the LLM uses to decide when to call this specific tool. Inside the handler, we write the actual logic, such as a database query or a file system read. Because the MCP server can run locally on the same machine as the data, it maintains high security, no need to expose your internal database to the public internet. The protocol handles the serialization and communication via JSON RPC automatically. This simplicity allows teams to wrap their legacy internal tools in an AI-ready interface in just a few hours. With the code in place, we must consider the long-term impact on our overall system strategy and how this prevents being locked into a single provider. The ultimate value of MCP lies in its ability to prevent vendor lock-in and enable truly multi-model agentic workflows. As an architect, your biggest risk is building a massive library of tools that only work with one specific AI provider. MCP mitigates this by providing a universal interface. If a better, cheaper, or faster model is released tomorrow, you can point that new model's client to your existing MCP servers, and your entire suite of tools will continue to work perfectly. This interoperability is the cornerstone of a sustainable AI strategy. We are moving toward a world where intelligence is a commodity that can be swapped out, while context and tools remain the core proprietary assets of your organization. By adopting MCP now, you are future-proofing your RAG pipelines against the rapid shifts in the model market. Now that we have bridged the data gap with MCP and understood its synergy with RAG, It's time to assemble all these components embedding, vector DBs, and MCP into a single, bulletproof 2026 blueprint in the next chapter. In 2026, a production-grade AI stack is no longer just an LLM with a simple vector search script. We are looking at a highly integrated ecosystem where data ingestion, vector storage, and the model context protocol, MCP, act as a single, cohesive unit. At the heart of this master architecture, we have the ingestion pipeline utilizing tools like Apache Flink for real-time stream processing, feeding into high-performance vector DBs like Milvus or Weaviate. The inference pipeline is where the magic happens. It doesn't just query a database, it uses MCP to dynamically discover and execute tools across your entire enterprise infrastructure. This integrated approach ensures that the model always access to fresh context, the delta between what was trained and what is happening right now in your SQL databases, Slack channels, or Jira boards. Architects must view this as a modular engine where every component is replaceable, but the interfaces are standardized. But having all these components is just the start. How do we ensure they actually talk to each other fast enough for a production user? Question. Let's look at the latency reality in the next scene. Analyzing the request-response lifecycle is critical for maintaining an enterprise-grade latency budget. In 2026, users expect near-instantaneous responses, yet the complexity of a RAG MCP stack adds multiple points of failure and delay. The process begins with query embedding, which often takes 5,200 ms depending on the model provider. Then comes vector retrieval, where top case search and re-ranking can add another 100 ms. The most significant variable is the MCP tool execution phase. If a tool needs to fetch data from an external API, your latency could spike. To manage this, we implement asynchronous tool calling and speculative execution where possible. Furthermore, cost management is handled at the gateway level, routing simpler queries to smaller models and reserving the high-cost, high-reasoning models for complex MCP synthesis. By monitoring the token-to-latency ratio, we can optimize the stack for both performance and profitability. Speed and cost are vital, but without a robust security framework, this high-performance engine becomes a massive liability. Payoff. This brings us to the most overlooked layer of the stack. Security and governance are the bedrock of any system operating in 2026. As we integrate deep into enterprise data through MCP, the attack surface expands significantly. We address this using a 4-layer security stack. At the foundation is infrastructure, security, VPC, isolation, and IAM roles. Above that, the data governance layer enforces metadata-level RBAC, role-based access control, within the vector DB, ensuring a user never retrieves information they aren't authorized to see. The MCP gateway layer is where we apply strict permission scopes for tool execution. Just because an LLM can call a delete record tool doesn't mean it should for every user. Finally, the application layer handles identity federation. We must treat every MCP tool call as a potential security boundary, applying the principle of least privilege to both the model and the tools it consumes. Once the architecture is secure and functional, the next challenge is making it survive day 2 operations when traffic spikes 100-fold. Teaser scalability isn't just about more servers, it's about a different architecture altogether. Scale horizontally or fail. That is the mantra for AI systems in 2026. For the vector DB, we move beyond single-node instances to distributed sharding and read replicas. This allows us to handle billions of embeddings while maintaining subset search times. For the MCP layer, we deploy stateless tool servers in containerized environments like Kubernetes, allowing them to autoscale based on gRPC or WebSocket load. We must also distinguish between in-memory indexing, which is fast for frequently accessed data, and disk-based indexing for massive, archive-level datasets. In practice, many enterprises are adopting serverless vector databases to offload the operational burden of sharding and rebalancing. This scalability pattern ensures that as your document count grows from thousands to millions, the system's responsiveness remains linear. Scaling the infrastructure is easy compared to scaling the visibility. How do we debug a system where the failure might be hidden inside a latent tool call? Question. Let's look at the observability requirements next. Observability in a RAG and MCP-driven stack requires a departure from traditional APM metrics. It is no longer enough to know the CPU usage. We need traceability across the entire reasoning chain. Our checklist for 2026 includes semantic traceability, tracking exactly which document chunks were used for which LLM response. We must monitor retrieval precision and hallucination rates using automated evaluation frameworks like Regus or Rise Phoenix. For MCP, we need detailed tool execution traces to identify if a bottleneck is in the LLM's reasoning or the external tool's latency. Tracking context window saturation is also vital to prevent lost-in-the-middle phenomena, where the LLM ignores critical data in large prompts. If you can't measure the quality of the retrieved context, you're essentially flying blind. This observability framework is what separates an experimental prototype from a production-grade autonomous agent. Payoff. But where is this all heading? Let's conclude with a look at the future of this architecture. We are moving from passive RAG systems that simply find information to autonomous agentic workflows that execute tasks. The architecture we have built with MCP at its core and a robust vector backbone is the foundation for this transition. By 2026, the RAG pipeline will be viewed as the short-term memory of a much larger agentic brain. The blueprint we've discussed provides the modularity needed to swap LLMs as they improve or upgrade MCP servers as new enterprise tools emerge without rewriting the entire stack. Future-proofing means designing for interoperability. By adhering to standards like MCP and OpenTelemetry, your system remains resilient to the rapid evolution of AI models. This is how you build a system that doesn't just survive the next wave of AI but thrives in it. Now that the blueprint is complete, it's time to turn this architectural vision into reality. Bridge, let's move to our final chapter, the implementation checklist, where we turn these concepts into a step-by-step deployment guide. As we wrap up our journey toward the 2026 AI stack, it is crucial to establish a concrete execution plan. In the first 30 days, focus on quick wins. This means auditing your current RAG pipeline for retrieval bottlenecks and mapping out which external data sources require MCP integration for real-time access. By day 60, your architecture should shift from simple retrieval to an agentic workflow, where MCP servers provide the standardized interface for your LLMs to act upon the world. Finally, by day 90, the goal is reaching operational maturity with automated semantic evaluation and dynamic embedding updates. This 90-day roadmap ensures you are not just building a prototype, but a production-grade system capable of handling the complexities of next-generation enterprise AI. But how do we know if the architecture we've built is truly ready for the rigorous demands of a 2026 production environment? Let's look at the ultimate architectural filter. This final checklist represents the standard for any high-performance AI system designed in the mid-2020s. First, verify your MCP protocol compliance. Is your server truly decoupled from the client to allow for modular scaling? Second, assess your vector database cost-to-performance ratio. Ensure you are not over-provisioned for your current recall requirements. A 2026-ready stack must also include robust observability for embedding drift and a clear strategy for cold start data ingestion. Remember, the most elegant architecture fails if it cannot handle the long tail of edge cases inherent in human-AI interaction. By following these rigorous standards, you move beyond the brittle RAG pipelines of the past and into the era of reliable, tool-augmented intelligence that drives real business value. You now have the complete blueprint for the 2026 AI stack, from the lowest level of embeddings to the orchestration layer of MCP. The architectural patterns are clear. The only question remaining is how fast you can implement them to lead the market.